All right, Team Fantastic. We're back on our Topic 5 Antiderivatives and Integration Adventure in AP Calculus AB. We spent the last couple classes first learning about antiderivatives and then having a quick chat at the end of last class about the idea of differentials. And it actually goes a little bit further last class than anything you need to know. So again, no stress there, but we are going to pull that concept of a differential into class today. And we're going to use the idea of differentials to actually help simplify our antiderivative process. But before we get there, we need to remind you of one other topic that you may or may not have seen in the past. If you had me for Trig Pre-Calc, we used U-Substitution to solve trig equations. In fact, some of your teachers might have even shown you U-Substitutions to help you factor way back in the day. But if you've never seen a U-Substitution before, I will show you right now. Traditionally, people use the variable u. You can use any variable. When you get to Calc AB or Calc 2, you'll use both u and v, but you can use anything you want, except maybe x, because there's already an x there. So enough meandering. Let's go ahead and jump into this. There's a quick opener here, and even if you're not sure how to do u substitution, let's see what you can work out here. So your goal is to solve this equation here. And as a reminder, to solve trig equations, although it is, and I'm going to erase this, just giving you a heads up in case you wanted to write this, I would suggest you don't write this. Although it is an option to use the inverse trig function to undo a trig function, we tend not to want to do that when we isolate x, because this will get x alone. This only has one answer. Inverse trig functions are only allowed to have one output because otherwise they wouldn't be an inverse trig function. But the issue is there are an infinite number of answers that can make this true because sine is cyclical, it repeats itself. So the question really becomes, how can we solve or determine what x is and still find every solution instead of just a single solution? So that's a little bit tricky. But if you remember our U-substitution process, go for it. If not, that's okay. You can still give this a shot, and I bet you'll be able to come up with an answer or two. And then once you've given it a good shot, go ahead and unpause this video, and I will take you through the process. Okay, hopefully you had some idea of where to start. If you didn't, that's okay. But here's what we're going to do. The trickiest part of this problem is the 3x that's inside of sine. So what I'm going to do is temporarily remove or replace that 3x with something more simple. The point of a U-substitution is to take a complicated expression and make it more simple. So in this case, what I'm going to do is state what my U-substitution will be. So what that's going to look like is I'm going to say we're going to let, and I always do a cursive L in let. I don't know why. I think I had a professor that did that or a high school teacher. Plus, cursive L's are so pretty. So let u equal 3x. We want to guide the reader through our process here. So what does that mean we've done? Well, we're going to take, instead of sine of 3x equals square root of 2 over 2, we're just going to say let's let a single variable sit in there. Now this variable is standing for a more complicated expression, 3x, but it's going to temporarily simplify what we're trying to solve for. Once we're here, this isn't too terrible, because now it's just saying sine of what single thing is equal to square root of 2 over 2. And hopefully at this point in your math careers you know at least one of these solutions. I'd prefer both, but at least one is okay. We need to remember, of course, that sine is the y, and the y-axis is positive in these first two quadrants. So the answer to this is going to be some sort of rotation in the first quadrant and some sort of rotation in the third. And we also need to start recognizing that this root 2 over 2 comes from when we do pi over 4 multiples. So we can determine then that u is equal to pi over 4, or u is equal to 3 pi over 4. Both of those will create triangles up here that are 45, 45, 90 triangles, with the y-axis being positive. But unfortunately, we're not done. And we're not done for a couple reasons, actually. First, we haven't listed all of the solutions, and that's what they asked us to do here, right? And to list all of the solutions, we need to remember that this yellow triangle I did will occur every 2 pi, every circle that we go. So if it recurs or happens every 2 pi, then I should be able to do plus 2 pi, and I use the letter k. Some people use n, some people use r, whatever works for you. But basically this is telling us every 2 pi, we get back to the same spot, and that will be another solution. And then same thing for 3 pi over 4, right? Every circle that we go, we'll circle back to the same spot, we'll create the same triangle, and so we need a plus 2 pi k over here as well. Well, great. But we're still not done. And the reason we're still not done is because we weren't trying to solve for u. We wanted to list all the values of x. And u is not the same as x. U is the same as 3x. So at this point, I'm actually going to go ahead and split my paper over here, and we're going to look at each one of these separately. Instead of u, though, we are going to replace the u with 3x and end up here. And then, of course, same thing on the other side, but I'll use purple for this guy over here, and we're going to do 3x equal to 3 pi over 4 plus 2 pi times k. Well, now I've almost solved for x. That's a little confusing. Now I've almost solved for x, but we still need to isolate x, and we do that by either dividing by 3 or multiplying both sides by 1/3. So multiplying by 1/3 will give us pi over 12 plus 2 pi over 3 times k. And then on the other side, we end up with x equals, and if you multiply by 1/3, although yes, the 3's would cancel and leave you with pi over 4, I'm actually going to put this as 3 pi over 12 as well. I know it reduces, and that's just so all of our answers end up being over 12, and it looks like the answer solution on the other side. So together, these two answers are listing every solution of x that will solve our original equation. There was a last step, and honestly, at this point, if you don't want to hear the last step, you can skip down to the calculus part. This is just a nice review of trig in case you want it. The last part, though, asks to list every solution on the interval from 0 to 2 pi. And the way we do that is I'm going to keep a running tally down at the bottom here, and I'll do the same thing on this purple side. And what we do is we just start ratcheting up through values of k. So I'm going to start with my lowest value of k, which is going to be k equals 0. Now before I do that, I'm eventually going to have to add these fractions together, and you might notice that there's an issue in that they don't have a common denominator. So I am going to take a quick second and give common denominators over here. 4 is going to be 8 pi over 12k. And that looks pretty good. So we're going to go ahead then and start just picking values of k. When k is 0, x becomes pi over 12 plus, well, that all becomes 0, so we just get pi over 12. Pi over 12 is certainly on the interval from 0 to 2 pi. It'd probably be like right here. So pi over 12. Cool. Then we have k equals 1. This becomes x equals pi over 12 plus 1 times 8 pi over 12, which is just 8 pi over 12, and that gets us 9 pi over 12. So that one is good as well. And yes, I realize you could reduce 9 pi over 12. That's 3 pi over 4, I think. But you don't have to. So we're going to keep going through here, but I think we can see the pattern. We went from 1 to 9 because we had to add 8. So when I do k equals 2, right, this is going to be x equals pi over 12 plus, now I have 2 of these guys, wrong one. We have 2 of these guys, which is going to be 16 pi over 12. And so that ends up with 17 pi over 12. So 17 pi over 12 is good as well. Okay, now we have to think about that reducing again, because we only went from 0 to 2 pi. And so if I thought about that 2 pi or 2 pi over 1, is this bigger than 2 pi? Is that outside the interval? Let's convert 2 pi to be 12. So to multiply by 12 over 12, oh yeah, 24 over 12 is 2 pi. So as soon as this fraction exceeds 24 pi over 12, then we've listed all the solutions. And we said that we're just adding 8 pi over 12 every time. So I think I can just do 17 times 8, or 17 plus 8 to get my next one, which is 25 pi over 12. So that is a solution. It's just not on the interval, so we don't need to list it. Usually there is symmetry. If there are 3 solutions here, I should expect 3 on the other side as well. In fact, because there were originally 2 solutions, but we have this 3 inside, now we're going to have triple the number of solutions, and I should expect 6. We got 3 over here, which means there are 3 left. We'll do that same step again, 3 pi over 12 plus 8 pi over 12k. And then we're just going to do this one faster. When k is 0, we end up with 3 pi over 12. When k is 1, we're just adding 8 pi over 12 every time, so it becomes 11 pi over 12. Add 8 more, 19 pi over 12. There are 3 more solutions, and we now have our 6 solutions that occur from 0 to 2 pi. What was the main point of this? The main point was to show you what a U-substitution does. However, a nice trig review isn't a bad thing since many of you do struggle with trig. The more you see it, the better you're going to get. Okay, let's get back into the calculus realm. I mentioned before that generally when you do a U-substitution, it's your goal to make the thing you're working with, whether it's a trig function, an integral, a factoring problem, your goal is to make it look easier. So what we're going to keep in mind is that as we go through, we're going to try to replace the most complicated part of our expression with u. We're also going to be looking for a function that has x to some power, where that power is 1 larger than another power in the problem. And that will make more sense in a bit. We'll come back to this a bunch. So to use a U-substitution, we use differentials, which we learned last class, to rewrite the interior of the integral. Now don't freak out, you're like, oh my gosh, integrals, or differentials, they were so confusing. It's really, really easy to do. Okay, so if we wanted to go the long way around, just another look at the differential, and this is probably the more mathematically rigorous, what we're going to do is leave a little space on each side here. We're going to take this problem, let u equals x squared plus 2x. And they're asking us to find du, which is the differential of u. So I'm going to do d of this side and d of this side. Okay, well, d of u just becomes du, which we're trying to find, so that's very nice. D of this side, well, d of x squared becomes 2x to the first times dx. And then this 2x at the end, 2 is a constant, but the differential of x becomes dx. Of course, I think I noticed something in common to both the terms at the end. 2x and 2 both have a dx in common, and I'm going to factor that out to the end. Of course, you could factor this out to the beginning, but you'll see that won't make a lot of sense, or it makes more sense to do it the way I did here. Now, again, I promised this was the longer way around, which is a good thing because this was only 2 steps. And now we're going to look at a quick shortcut. If we wanted to find du of this, couldn't we do it faster? Certainly. Because you'll notice that this du is made up of 2 parts. It's made up of the derivative of this, 2x plus 2, and it is also made up of a dx. And we actually defined a differential last class as the derivative times dx. So how do we do it faster? Well, here's what we're going to do pretty much every time. If they ask you to find du, then we're going to say, okay, we're doing d of each side. That's going to give us du. And then we just take the derivative, 2x plus 2. We've been doing that for months. Hopefully we can do the derivative of x squared plus 2x. And then we multiply it by dx. Done. That's how easy our differentials are going to be today. We take a quick derivative and we write dx at the end. Seriously, that's all. My dog just barged into the room and then had the audacity to look at me, turn around, and leave, and left the door open. Oh, man, all of his training that I haven't done has just gone to waste. Okay, now, let's actually use U-substitutions in the context of calculus. So, how do we do that? Well, let's take a look. We are asked to find the antiderivative of x squared minus 9 times 2x, and this is important, times dx. This dx is technically multiplying at the end. It's this infinitely small quantity. Now again, we can really treat these as just the whole integral process, and it doesn't really matter at this point what the dx means. It does have meaning that we'll go more into visually later on. But we have all this multiplication stuff. And the multiplication is a big problem because we have one expression with x multiplying by another expression with x, and we don't have product rules for integrals. We're like, oh no, what do we do? Well, one option is you could multiply x squared minus 9 times itself 3 times, and then distribute in 2x, and then find the antiderivative, but that sounds terrible. So instead, we're going to simplify this problem. And I had mentioned earlier that to do a U-substitution, we usually try to set u equal to a function that has x to some power, where that power is 1 larger than another power in the problem. So looking down here, I see a couple powers. I see a third power, a second power, and a first power. Now, u isn't going to be this random exponent. U is going to be something with an x in it. So really, we have two options for a u substitution. We can substitute u to be x squared minus 9, or we can substitute u to be 2x. Looking at this, though, I see a square which is 1 larger than another term with x. We do not want to do u equals all of this because this 3 is not 1 larger than something else in the problem. You're like, what is 1 larger than 2? You're right, but that's all going to get enveloped by the u, and now 3 is not 1 larger than 1. And again, this will make more sense as we go through. So u equal to x squared minus 9. Cool. Well, let's take a look at what we have for that integral then. Integral-wise, we replaced x squared minus 9 with u. We're like, woohoo, we're crushing it so far. What's still there? Well, there's still a 3. I said change colors. There's still a 3. There's still a 2x, and there's still a dx. And so when we perform a u substitution, we need to make sure that we change every instance of the original variable, and we replace every instance with the new variable. And you might notice that there's not just one x left over, there are 2. There is both an x here and an x at the end, and that is no good. We need to somehow replace both of those x's with u's. And the giveaway is that this x is attached to a differential, dx. So in order to replace the x, we're really going to have to replace the dx as a whole, which means we need to replace a differential, which means we need a differential. So the process for a u substitution is step 1, decide on what u is going to equal. And then step 2, find its differential. So we're going to do du, which means we have to do d of x squared minus 9. But as we saw, that's going to be very easy because we just do the derivative of x squared minus 9, which is 2x minus 0, so we'll just call it 2x, and then we throw a casual dx at the end. Okay, cool. There is my differential. Now, how does that help? Well, we have 3 different factors here, 1, 2, 3, okay, and we need to compare and see what this looks like in the original function. Well, I see 2x dx. Oh, look. I coincidentally see 2x dx over here, don't I? Cool. So can't we replace 2x dx with du? It says du is equal to that, doesn't it? So we get the integral of u cubed times, and then instead of 2x dx, we're going to replace that with du. Wow, that looks way easier. So now instead of trying to find the antiderivative of this whole guy, through u substitutions and a little bit of cleverness, we have a much easier integral to perform. So let's do that. The antiderivative of u to the third power is going to be u to the fourth power. My pen is really struggling here. Sorry, guys. U to the fourth power. And, of course, we need something to offset the 4. So that's going to be a 1/4 out front. Plus, oh yeah, plus c. That's the one. So we went from here to here to here. So are we done? Well, no, we wanted the antiderivative in terms of x. So just like the trig problem on the opener, we do need to go back through and replace u with what it originally equaled. And u, of course, was originally equal to x squared minus 9, right? We saw that up here. And then we still have the fourth power plus c. Very important, we are going to check our work, and we're going to do this on most of these to make sure we didn't just do some black voodoo magic that doesn't actually work when we check it. So when we check our work, we are going to take the derivative, d dx, of 1/4 x squared minus 9 to the fourth. We leave off the plus c because that goes to 0 anyways. So let's see, the 4 comes down, that just becomes a 1. X squared minus 9 stays the same, reduce the power by 1, times chain rule. Derivative of x squared minus 9 is 2x, and so cleaning this up, I see x squared minus 9 cubed times 2x. Does that match the integrand at the beginning? If we look here and look over here, I think these do match. Go us. We have crushed it. Sometimes I get the question, wait, does the dx just disappear here? And yes, it does. At least for now, we're going to say that when you do the integral, the dx does disappear when we get back to the original antiderivative. Now, that might have gone over some of your heads and seemed incredibly confusing. It goes much faster than this the more you practice. I unfortunately cannot cover every single time of how I know when to do U-substitution. And honestly, sometimes I still get it wrong. I'm like, ooh, maybe U-substitution. It doesn't work. And I'm like, not U-substitution. That was unfortunate. But I will give you some tips and tricks. So let's look at this next problem. One giveaway you'll need to use U-substitution is when you have a factor with x multiplying by another factor with x. Because we don't have a product rule, there's got to be another way to do it. And it's rare but possible that there are other ways on the AB exam, but there aren't too many others, and we'll cover those in later classes. The second giveaway that it's going to be U-substitution is looking at this complex part here and seeing a power that's 1 greater than the x to some other power. Again, we're not going to do this cube root. The derivative, which we'll have to do with our differential of a cube root, is gross. I want a simple U-substitution that takes away some of the complicated part but has an easy derivative. And so what I boxed there is an easy derivative. This is an ugly derivative. So let's start with the one that's 1 larger than the other term, which means that u is going to be 1 minus 2x squared. We know we're also going to need a differential. Okay, so our du, in this case, 1 becomes 0. We get negative 4x, and don't forget your dx at the end. This is looking pretty darn good. So let's go through. We have the integral of the cube root of, we replaced all of this with u, and then negative 4x dx, look at all this at the end, is going to get replaced with du. That is way more simple than the original integral. However, in order to actually do this integral, we should probably rewrite our cube root as a 1/3 power, and then we work the rest. Add 1 whole to the 1/3 power, which gives us 4/3, offset the 4/3 with 3/4, plus c. Last but not least, don't forget to replace that u with what our original substitution was, 1 minus 2x squared to the 4/3 plus c. And that's as far as I want to go. Great. So again, it gives us a way to simplify the integral to get the answer. Now, some of you will look at this and said, but I could have guessed and checked to get that answer. Like, I'm pretty sure I know the chain rule really well. I know that we're going to have to add something. I can get there without doing a U-substitution. And that's brilliant. However, what we're going to find is the AP exam wants you to know how to do U-substitutions. There are certain scenarios that it's vital in order to be able to do a U-substitution that aren't always available in Calc AB. So the way they make sure that you can do a U-substitution is, instead of saying, here's this, find the answer, they say, here's this, which one is the correct U-substitution, and this will be a multiple choice answer. So they'll force you to do U-substitution. So you do actually need to know this, even if you're looking at example 3 and you're like, but I can figure this out without, doing a U-substitution. I understand. Just practice it for a bit. It will not be bad. Now, for the rest of these, I'm going to really suggest that you try to do it before I explain how to do it, because no matter how many times I show you the right way, it's not going to click until you fail. And that kind of seems weird, but I mean, it's a true thing. Like, imagine you're playing a video game and you try something and it doesn't work. Well, good. Now that's going to remain in your brain. You're like, whoop, that pathway didn't work. I need to try something else. It's the same thing here. If I lead you to the exact answer every time, you're never going to know what the wrong answer looks like. And when I release you back into the wild, you're going to struggle on this quite a bit. So please, 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 at this point, pause the video and see if you can figure out what the U-substitution is and what the du is. And honestly, try to figure out the whole antiderivative. If you can do that, and then unpause and check the solution, that's great. And honestly, I would unpause, fast forward to the solution, and make sure you got it right. If you did, move on. There's probably no reason to listen to hear me go on through these, because there are a bunch of examples that we're going to go through, and you will go through them much faster than me just talking you through. So turn 60 minutes into 30. go ahead and pause me. And hopefully now you've unpaused and been successful. Let's get to it. I'm certainly not going to do a fourth power for a U substitution because I don't see a third power, right? And the reason we're talking about one power smaller every time is because whatever you do for a U substitution, you have to do the differential, which includes the derivative, and the derivative will always reduce the power by 1. So whatever power you see here, you must see a power that's 1 smaller than that somewhere, otherwise your U substitution won't work. But then you're like, wait, there's no cube. What do I do? Don't forget, though, there's a first power here and technically an invisible x to the 0th over here. So I'm feeling a U substitution of 1 plus 2x. And then we look at du. 1 becomes 0, 2 is multiplying, and then x becomes dx. Aha! Now I see a U substitution, and I see my du. So let's go ahead and work this integral. So we're going to go u to the 4th power times, let's see, 2 dx becomes du. Okay, antiderivative, we got this. Add 1 to the power, offset the power, plus c, and then replace your u substitution. 1 plus 2x to the 5th plus c, and we are good. Yes, you should check this. This check is pretty easy, though. The 5 comes down, cancels out the 1/5, becomes a 4. That's the first part. And then the chain rule, this 1 plus 2x multiplies out at the end, and you get a 2. Cool. Example 4. Uh-oh, this one looks intimidating. It had e's and y's and y. Literally. So looking at example 4, what do we do here? Well, definitely a U substitution because I see a term with y multiplying by another term with y. So what's our U substitution going to be? Well, I know what it's not going to be. We don't want u, and I'm going to erase this, to be e to the 4y squared minus y. And you might be looking at this saying, well, why wouldn't we want that? There's this square up here, and that's 1 bigger than a first power. You're right, but if you include the e, what do you remember about including an e? Doesn't it stay exactly the same? So there's going to be another e down here with a dy times that derivative. It's much too complicated. Instead, just take the power, where our power is going to be 4y squared minus y. And then our du is going to be, let's see, this derivative is 8y minus 1. All of this derivative multiplied by dx. Of course, then you might say, well, wait, I'm sorry, times dy. This is with respect to y, isn't it? But then you might say, well, wait, though, there is no 8y minus 1 times dy. Sure there is. There's this 8y minus 1, and then the dy over here. This is all multiplication, so it might make you feel better if we rearrange this a bit. I'm actually going to take this 3, it's a constant, and move it out front. I don't think it's going to affect our antiderivative. And then I'll rewrite that e to the 4y squared minus y. And then I'll put the 8y minus 1 and then the dy. And you're completely allowed to reorganize multiplication in any order, and that's all we did here. And now I think our u substitution might make a little more sense. 4y squared minus y is our u. 8y minus 1 dy is our du. Get colors in there. And cool, now we have a pretty easy antiderivative. The antiderivative of e to the u with respect to u is just itself. It's just e to the u. And then don't forget your plus c. Finishing this off, 3e, our original u substitution was for 4y squared minus y plus c. All right, hopefully you guys are getting the idea of this and seeing that this differential process is really not hard, just a derivative and throw a d something at the end. So let's go ahead, pause me, try example 5, and then we'll unpause and discuss. All right, hopefully you found some success here, but this one is a little bit trickier. The u substitution, hopefully at this point, is a little bit more apparent. You're like, oh, there's an x cubed and an x squared. I bet we're going to do a u substitution for x cubed plus 5, and you would be 100% correct. And then our du, easy again, 3x squared times dx. All right, let's do some replacements here. First, I am going to reorganize this. I'm going to put the x cubed plus 5 to the 4th first, and then x squared, and then dx. All right, substitution-wise, we have u to the 4th times, wait a second, I see a 3x squared dx, and there's no 3 up here. Uh-oh. Well, we can't replace that. They are not equal. But luckily, we know a little bit of algebra, right? And that little bit of algebra should help us manipulate our differential. If we don't want there to be a 3 there, then don't have a 3 there. Let's move the 3 to the other side. Now, you can divide both sides by 3. That is acceptable. I've found, though, that it's much easier to multiply by the reciprocal than actually divide. So to multiply by the reciprocal, I'm going to multiply both sides by 1/3. And so this gives me that 1/3 du is equal to x squared dx. And now I think we're in business. X squared dx, x squared dx. We can replace that not with du, but with 1/3 du. There we go. Once we're here, you could do the antiderivative. I'm going to factor out that 1/3 again, though. That's just a constant. And then we can work with this u to the 4th du. So 1/3. Antiderivative of u to the 4th is, of course, u to the 5th. To cancel out that 5, we need a 1/5 plus c. And then simplifying down a bit, a 1/3 and a 5th make a 15th. U, our original substitution was for x cubed plus 5 to the 5th power plus c. Bam. And then maybe you can even see where that 1/15 gets canceled out, because we certainly don't have it up here. When you do that derivative, right, and maybe it's worth showing this derivative really quickly. If I wanted to do ddx of 1/15 x cubed plus 5 to the 5th, the derivative, the 5 will come down and it will reduce. We have 5/15, right? That will become 1/3 x cubed plus 5 to the 4th power, but then times the derivative of the inside, so times 3x squared. But then simplifying further, 3 and 1/3 are going to cancel, and that's where we get that x squared times x cubed plus 5 to the 4th, which does match our original integrand over here. Okay, so really you learned everything you need for U-substitution. These last couple problems are just a few tips and tricks as you go through. The only really tricky thing with the U-substitution is sometimes your differential won't match the original, but just bring in some algebra, manipulate both sides until it does match, and you're gold. So let's try these last couple. Okay, 6. Well, hopefully you just gave it a shot. If you didn't realize I was pausing for you, then try it again. And here we go. Well, let's see. U-substitution, because we have one thing multiplying by another. We certainly don't want to include cosine in our U-substitution, because if that's the case, then there'll be a sign in the differential, and there's certainly no sign here, so that's no good. So it really comes down to a U-substitution for this guy or for this one. Thinking about the differential, which one, when you take the derivative, will give a result of the other? And hopefully you're saying, ooh, if you do the derivative of the second one, w becomes 1, natural log of w is 1 over. I bet our U-substitution is going to be for this guy. And it's all about the differential here. That should be a minus. Our differential, du, the derivative of w with respect to w is 1. And natural log of w is 1 over what's inside. And remember, our differential is defined as the derivative times the differential. And that is pretty handy. We have this guy times this one at the end, which we can replace. We'll do this all in one fell swoop this time. We have cosine of u, and then times dw1 minus w. These guys together just get replaced with du, and life is better. Antiderivative of cosine. Remember, our derivative rules say when we do the derivative of something starting with the c, it's negative. The antiderivatives, that's not true. In fact, it's the opposite. If you do the antiderivative of something starting with the c, it will be positive. So this becomes sine of u plus c, because of course the derivative of sine is positive cosine. And then we replace our u with what it was originally substituted for, which is that w minus natural log of w. Ta-da! Couple to go. Ooh, Nelly. This one looks tricky. Okay, well, let's just have at it. What makes this problem tricky? Well, a lot of it. And you might say, well, couldn't we bring this up to the top? And I would say, don't write this. I'm going to erase this after I do it. And sure, you could. In fact, I will move the 3 out front. I think that's not going to affect anything. You could write this as 5y plus 4 times dy, and you're like, to the negative first, right? If we bring that up, it was to the positive first, now it's to the negative. And you're like, oh, I can just do the antiderivative. To do the antiderivative, we just add 1 to the power, a 0 with power. That's not good, because then the whole thing turns into 1. And 3 times 1, the derivative of that is certainly not this. This is this one weird guy where we have a negative first power. And it might be easier if we kind of simplified down what we were dealing with, right? If we were just dealing with 1 over y, getting rid of all the extra constants, we should know the antiderivative of 1 over y. It's natural log. And so what we're going to do here is we are still, I like the idea of factoring out this 3. I think it's not going to affect anything. We are still going to try and simplify this down, but we're just going to simplify the denominator. We're going to try to make it into something where we can take the antiderivative. So we're going to say let u equal to 5y plus 4. This will give us a du of 5, 4 goes to 0, and then y becomes dy. Checking our problem, we can, and I'll work this over here, we can certainly replace 5y plus 4 with u, but I don't have dy isolated. I can't replace dy with all of this because I don't have what dy is equal to. We can, though, multiply both sides by 1/5. And now this tells us if you see dy, you can replace it with 1/5 du. Let's bring that 1/5 out to hang with the 3 out front. And then we get 1 over u du. Much nicer now. Antiderivative of 1 over u is not the natural log of u, but it's very close. It's the natural log of the absolute value of u. Yes, you do need to include the absolute value. Plus c. And of course, finishing this off, we should probably remember that u is actually a stand-in for something slightly more complicated, 5y plus 4. If you take the derivative, can you see that there's going to be a chain rule of an extra 5 there that's going to cancel out the 5 down below and give you the answer? If not, try taking the derivative and then let me know if you get stuck. Okay, just a couple left. Secant squared of 4t times all that other stuff. Well, as before, you should maybe notice I'm missing a parenthesis. That's awkward. There we go. Sorry about that. Otherwise, this problem would be very tough. Okay, go ahead, see what you can do, and then we'll get back together. Now this one is intended to throw you off. You might see a 2 and you say, oh, the 2 is going to reduce to a 1. It doesn't quite work that way. We need to be really good with our trig derivatives here. And in particular, we need to remember that the derivative of tangent, which we'll need to do for the differential, the derivative of tangent is secant squared. So I'm feeling a U-substitution for this guy. U equal to 3 minus the tangent of 4t. What does that give us for du? 3 becomes 0. There is still a negative here. The derivative of tangent is secant squared. 4t stays the same. Chain rule, the derivative of 4t is 4. And then don't forget that differential hanging out at the end. This one may also benefit from rearranging a bit, so I'm going to do that. We have this 3, and let's do the U-substitution right now, just so we keep in mind what's happening. So this is the third power, but then there's still a secant squared of 4t times dt. Is that what I have here? Do I have secant squared of 4t times dt? Well, kind of, but I see some extras. I see an extra negative and an extra 4 that certainly isn't up here. So let's get rid of those. Negative 4, to get rid, we can divide by negative 1/4, or rather multiply by negative 1/4. And that's going to leave us with positive secant squared of 4t times dt. Now we can do our last substitutions. We have u cubed. This guy all gets replaced with negative 1/4 du. And before we do that antiderivative, let's factor out any extra constants here. We have u cubed times du. Okay, u cubed becomes u to the fourth. To cancel out u to the fourth, we need another 1/4 there. And cleaning this up just a little bit, negative 1/16. What was our u originally for? It looks like it was for 3 minus tangent of 4t to the fourth power plus c. Oof, that was a pretty gnarly one. Actually, the derivative of that is pretty tricky. The 4 is going to come down and reduce it to 1/4, but then through the chain rule, you'll get another 4. There's a couple of negatives in there. Yep. Tricky. All right. Example 9. This one is wild because you look at tangent of x and you're like, why is this in the U substitution section? And of course, my suggestion would say, good, do it without a U substitution, please, and come back to me once you're ready. Oh my gosh, you're back already because you don't know how to do the antiderivative of tangent, because it's certainly not tangent squared with a 1/2 in front, right? And I'll show you why right now. And I'm going to erase this again. You might say, oh, it's tangent to the first power, so let's make it tangent to the second power, and then put a 1/2 out front, plus c, of course. Well, if you check the derivative here, the 2 will come down, it'll cancel that out, and you're like, woo, looking good so far, tangent stays the same, reduces, and you're like, crushed it, that's what I started with, but no you didn't, because there's a chain rule, and the derivative of tangent is secant squared. And this does not match what we started with. So after you dry off those tears and come back to our problem, we look at this and go, okay, well, how do we do it instead? Well, we might want to remember an identity for tangent. In particular, tangent is sine of x divided by cosine of x dx. Okay? So then maybe you're like, wait a second. I know the derivative of sine is cosine, but the derivative of cosine is also sine. I bet u is going to be one of those two, but which one? Which one? We don't want to get into trouble here. And so what I'm going to do is rewrite this quickly. And I'm going to rewrite this as 1 over cosine of x times the sine of x times dx. And then I'm going to do it wrong first. So everything I've done so far I'm keeping, but I'm going to do the wrong U substitution first. I'm going to do let u equal to sine of x. Right. Well, cool, pretty good. Differential's easy. That becomes, I'll do my consistent colors, du becomes cosine of x times dx. We're like, great, this looks awesome. I see all of those up there. But you actually don't. I don't see cosine of x being multiplied by dx anywhere, because technically these are over 1. The dx is in the numerator. Dx is not multiplying by cosine. Dx is only multiplying by sine. And so we won't be able to replace this anywhere, and then you'll be sad. So we don't want to pick sine for this. Strangely, now I'm going to do this correctly. Strangely, I'm actually going to pick my U substitution for cosine. And you might be looking at this and thinking, well, how do I know which one to pick? And there's two answers. Answer number one is, it's okay if you don't, just try one, and if it doesn't work, try the other. But the real answer is, I've done problems like this thousands of times. And the more you do them, the more you're going to understand which you should pick for you and which you shouldn't. Because there are certainly some good advice problems of like, always pick the u to be 1 power bigger than the other. But that doesn't hold true for every problem. It certainly wasn't here. Here we had to pick natural log. Here we picked 5y plus 4. That's pretty random. And here there was no, then we did the opposite of the powers. So these extra problems are just to give you extra practice and see this from a different perspective. But honestly, do your independent practice tonight. The more practice you get done, the better you're going to feel about this. And in fact, U substitution is important enough that in a few classes, we're actually going to do a whole nother lesson on it again just to get you more practice. So let's rock and roll. Let's do the correct U substitution this time. We're going to substitute for cosine of x, which means that our du is negative sine of x dx. But we have a bit of an issue because that's positive sine. So I think we should probably move the negative over to the du here. And that gives us sine of x dx. And when I say move, I really mean multiply both sides by negative or divide both sides by a negative. So now let's start replacing things. 1 over u times sine of x dx is going to be replaced with negative du. So I'll probably move the negative out front of this integral just to clean things up. 1 over u du. Negative's just hanging like, hi guys, I'm bringing you down. And then we have 1 over u, which we should be comfortable with that antiderivative. It's the natural log of the absolute value of u plus c. And as we finish this up, we're remembering that u is cosine of x. And I bet you would not have guessed that that is the antiderivative of tangent, would you now? But it's a day to be surprised. Okay, we have 2 examples left, I promise. See, those are the last 2. And then there are some dates down at the bottom, but again, that's pretty relevant for just my class, and not everyone watching this is in my class, so don't stress that. I will talk to you if it's relevant to you, and I won't if I won't if it is not. Okay, what do we do here? Well, I'm thinking that this looks more complicated than this, so I'm probably going to try that one first, right? Pick the more complicated piece if you have 2 pieces that look the same. So let's let u equal to 2 minus cosine of 1 minus x, and this is going to give us a pretty tricky du, and I'm actually going to do all the pieces. So 2 becomes 0, negative, and then cosine, the derivative of cosine is negative sine, so that's actually going to turn our negative there to a positive. Inside stayed the same though, so the derivative of the inside, 1 is 0, negative x is negative 1, and then don't forget the dx. So simplifying down a bit, we get that du, the negative is going to move out and hang with this sign here, is negative sine of 1 minus x dx. But there's no negative over here. If there's no negative, let's move the negative over here, just very, very similar to what we did last question, and now we're here. Whew! Okay, we did the hard part. Let's get to the easier part. This 2 minus cosine of 1 minus x to the 4th power was replaced with u, and then the rest of this sine of 1 minus x dx is replaced with negative du. Again, using that same trick, moving the negative out front just to make your life a little easier. And then antiderivative, u to the 5th, 1/5 to offset that, plus c, so negative 1/5, and then u to the 5th. Okay, well, u was that original 2 minus cosine of 1 minus x. Whew! Okie dokie. If you got through that, you are awesome. That is a definitely tricky question, one of the harder ones I've seen in a while. Of course, I said that, and now we get to 11. 11 breaks all rules. And it's weird because I've actually seen this show up maybe twice in the last decade on the AP exam. And you're like, oh, only twice. Well, twice is more than 0. And the fact that they put a problem like this on the AP exam is pretty rude. It's a tough question. And they were both multiple choice questions. They were like, okay, and they were a little bit nice because they knew it was tough. They're like, if we give you the U-Substitution, can you figure out this question? And I'll do the same for you. Strangely, this U-Substitution is going to be for x plus 1. So why don't you pause here and see if you can figure out the antiderivative if u is equal to x plus 1. And then unpause when you're ready. Did you get stuck, or did you get it? Well, let's see. Let's just go through our classic du. The derivative of x is 1, 1 is 0, and then times dx, which really just means that du is replacing dx. Cool, this actually seems super easy. So if we look over here, we have this square root, and we replaced x plus 1 with u, and then we replaced the dx at the end with du. So are we golden? I don't think so. We need to have replaced all the variables with u. And there's still this pesky x. And so originally we needed to do this because we had one function dividing by another where both had x in it. We don't have a quotient rule for integrals. And so here we're like, what do we do? Well, the nice part about this, and the trickiest part about this, is that we can manipulate our original U-Substitution equation. And this is the trick I would imagine 99% of people would miss, including me on my first time through for sure. If we manipulate this, we can actually isolate x. And if we subtract 1 from both sides, that gives me u minus 1 equals x. So looking at this U substitution over here and working it through a little bit more, I'm going to rewrite this as U to the 1/2 instead of the square root, right? That's usually a little easier for integrals. And then we're going to replace x with U minus 1. And then you're looking at that and you're like, okay, Mr. Grant is taking us in circles. How is this any easier than this? But shockingly, it is easier. And the reason it's easier is because, and I'm going to erase this again, so be careful here. If we have x and I move the square root of x plus 1 up, I'll rewrite it as x plus 1 to the negative 1/2. I am not allowed to distribute x in here because of this negative 1/2 power. You can only distribute when there's a first power. And so then we get sad because that would have helped us clean this up really easily. But look at what we've done here. We took the problem child, where the fact that there were 2 terms inside the 1/2 power, and we simplified it down to the fact that now there's only 1 term in there. And so if I try that same trick again, we keep u minus 1 to the first power, and then bring that u up to u to the negative 1/2, now we can distribute our single term into the multi-term. We can distribute this inside because we just have a first power, and you can get rid of it if it makes you uncomfortable, and we can simplify this down. So we have a first power over here, same base. Same base means we add the exponents. 1 plus a negative 1/2 is 1 minus a half, which is 1/2. And then this second term is pretty easy because anything times 1 is just itself. Don't forget that there's a negative there, though. So it becomes minus u to the negative 1/2. Still an integral symbol, and still this du hanging out like, hey guys, I'm still here. Cool. Now we can do the antiderivative of every individual piece because we don't have 2 functions multiplying or dividing by each other. They're subtracting, and that's totally okay. So let's get to it. Antiderivative of u to the 1/2, we add 1 whole to get 3/2, 2/3 to offset, minus add a whole to get positive 1/2, 2 to offset, plus c. Our original U substitution was x plus 1. So we have 2/3, I'll need a little more space here, times x plus 1 to the 3/2 minus 2 times x plus 1 to the 1/2 plus c. And again, this is one of those surprising ones where you look at this and go, that doesn't seem that bad, and then you look at the antiderivative and go, what did I walk into? Very, very tricky problem. There is one of these on your independent practice tonight. It's very similar to this one. I think maybe there's a minus instead of a plus, and I'll try to throw a couple more at you this semester. It is a weird little niche problem, and if it shows up on the AP exam and you don't remember it, I'm not going to hold any judgment against you, any grudges. It's a tricky question. Should you know how to do it? Sure. Should you study this every day until the AP exam? Probably not. There's about 400 other things that are probably more important than this. But this does conclude our U substitution for the day. So thank you for working so hard on this. We got through a whole bunch of examples, and I apologize for the long video. I am excited, though, to have you back for next class where the video is going to be like 15 minutes long, promise, because it's just going to be a couple U substitution practice problems, and you're going to crush it. All right, rock stars, I will see you for day 66 later on in the future.